Hello everyone. Today we're going to learn harmonically excited vibration, part 3. Here are the learning objectives for the whole chapter. Today we're going to learn how to find a response for viscously damped systems subject to basic excitation. So here we provide a mass spring damper system, but different from previously used mass spring damper system is that now it's connected to a bath. So the system has a mass M and has a spring and a damper over here. They're connected to a base. So instead of applying a force directly on the object, now in this system we assume the base moves. The first step is to do the force analysis. We draw this block and it's subject to two forces. So we take it out, and one force that is from the spring, the other force is from the damper. And how do we calculate the spring force? If the base moves. So the base moves up and down with the displacement of y. And this is how x moves. And we know that to find the force by the spring and the damper, it really depends on the relative motion of the two, relative motion between x and y. So if there is no relative motion, there won't be any force in the spring and the damper, right? So this is why the force created by the spring depends on the difference between x and y. If x is greater than y, say x moves faster than y, so the spring will be stretched. In that case, the force will be pointing downward. And the same thing if x moves faster than y, and the damping force will be pointing downward. So we can write the equation of motion by using Newton's second law. So mx double dot, that is equal to the summation of all the external forces, that is minus k times x minus y minus c times x dot minus y dot. And over here, y following a sine function, y that is equal to capital Y times sine omega t. Over here, capital Y, that is the magnitude, and the frequency of this base displacement is omega. Then we can rearrange it to make it in a standard form that we are familiar with. So we put x terms to the left, so that it becomes mx double dot plus c times x dot plus k times x. That'll be equal to the right hand side, which is ky plus cy dot. At the same time, we want to know what is the right hand side. Here we know that y that is equal to capital Y times sine omega t, and we can find a y dot that will be equal to y omega times cosine omega t. Then we can find a ky plus cy dot that will be equal to y times sine omega t plus c times y times omega times cosine omega t. And both of the two terms are harmonic vibration, right? So we have a sine omega t, cosine omega t, and they have the same frequency. It implies that we can combine them together and at a phase angle. So we know that it can be written in the form of a times sine omega t minus our angle alpha. So we know that it can be written in a form like this. Then we want to know, like, how do we write this form, and what is a, what is alpha. So we can simplify this term by taking out square root of squared summation of y sine, the coefficient of y squared k square plus cy omega square. So if I take that out, and then inside the expression that will be ky, let's call this term to be a. So ky over a times sine omega t plus c capital Y times omega over a times cosine omega t. And if further we define this as a cosine alpha, we define this cy omega over a as a negative sine alpha. And these two terms together, that becomes sine omega t times cosine alpha minus cosine omega t minus sine alpha. So it will become a times sine omega t minus alpha, right? So it also tells us what is a and what is alpha. So we know that a is equal to square root of that. So because both of the two terms have a y square, we can take a y square out. So that it becomes y times square root of k square plus c omega square. Since we know sine alpha and cosine alpha, so we can find alpha through this cosine and sine terms, right? Let's write it as tangent alpha first. So we know that tangent alpha, that will be equal to sine alpha over cosine alpha. Sine alpha, that is a negative c y omega over cosine alpha, which is a k capital Y. Y can be cancelled. So we'll write it as a negative c omega over k. You can also write alpha as the inverse tangent of a negative c omega over k. So next, what are we going to do? We're going to replace ky plus cy dot by what we found, a sine omega t minus alpha. So this is something we're going to do. We have the conclusion for this equation of motion. So mx dot plus cx dot plus kx, that is equal to a times sine omega t minus alpha. And over here we know that a, that is equal to y times square root of k square plus c omega square. And tangent alpha, that is equal to negative c omega over k, right? So we learned something similar to this, right? So let me write down what we have learned from last week. I'm going to use a different color. So we're going to recall what we had learned from last week. We learned the solution to mx dot plus cx dot plus kx, that is equal to f0 times cosine omega t, right? So we will learn the solution to this. We know the particular solution, or the steady state solution, that has the form of x times cosine omega t minus angle phi, right? And where capital X, that is equal to, do you still remember? F0 over square root of k minus m omega square plus c omega square. Do you still remember? This over here without an over divided by k. So the numerator, that is f0. And also the phase angle, that is equal to the inverse tangent of c omega over k minus m omega square. So this is what we have from last week. Now we want to compare between these two. So what's the difference? So last week we have a cosine function. This week we have sine function. So that should not affect the answer. So that will affect the answer here. So that will change this cosine function to sine function. That will be the difference, right? And at the same time, another difference is this phase angle. So over here we have minus alpha. We don't have a phase angle there. So that is the difference. So now it implies that for us to find the particular solution, in addition to this, it'll need another phase angle, which is a negative alpha. So that tells us by comparing the two, we can find the particular solution xpt that is equal to a form of x times cosine omega t. So I'm going to give it a intermediate angle phi 1 instead of phi directly, minus this angle alpha. This angle alpha, negative alpha, is inherited from the input here. And this phi angle is similar to the phi angle that we had from last week. That should have the same form. So over here, we know that if we do this, and x, that will be equal to, instead of f0, now the magnitude is a, right? So the magnitude is a instead of f0. So we replace f0 by a. The denominator, that is the same. So which is a k minus m omega squared plus c omega squared. We can further replace a by the formula we have. So that is a y times square root of k squared plus c omega squared over square root of this long term, k minus m omega squared plus c omega squared. And at the same time, the phase angle phi 1, that should have the same form what we had before, right? So that is the inverse tangent.
That's right. I think you're missing a square on the m omega squared, k minus m omega squared.
Yes, you're right. And also here we mentioned that it should be sine, right? So that should be a sine because we have a sine function. So that's something I forgot to change. So xpt, that is equal to x times sine omega t minus phi 1 minus alpha. So phi 1, that should have the same form, which is a tangent inverse of a c omega over k minus m omega squared.
Professor, if you use a cosine function for the particular solution, would it change the signs of the stuff or no?
So the reason how we change that to sine is because the input over here, that is a sine function. All right, so now we have a solution already. Then we want to do a little bit more to know like physical results that we can derive from the solution that we have from here. So let's copy the solution that we have from the last page. So we have mx double dot, the equation of motion plus cx dot plus kx. That will be equal to a times sine omega t minus alpha. A, that is equal to y square root of k squared plus c omega squared. Alpha, that is equal to inverse tangent of negative c omega over k, right? And also the static solution xp, that is equal to capital X times sine omega t minus phi 1 minus alpha. And here x, that is given as y times square root of k squared plus c omega squared divided by this long term, right? So that is a k minus m omega squared plus c omega squared. Let's start from the phi 1 minus alpha. So this is what we had from last page. So phi 1, we already know that is the inverse tangent of c omega over k minus m omega squared. So this is what we have so far, right? Then the next we want to know like what is the amplitude ratio. So the amplitude ratio will be defined the capital X over the amplitude of the input. So y over x, x over y, that will give us square root of a k squared plus c omega squared over k minus m omega squared plus c omega squared, right? Next, we want to write it in terms of the frequency ratio. So we divided k on both sides, both the numerator and the denominator. The numerator will be we divided by k. So when we divide it by k, we put it into the under the square root sign, so that it becomes 1 plus c omega over k squared, right? And the denominator becomes 1 minus m over k times omega squared plus c over k times omega squared. Over here, we're going to use some of the conclusion that we had before. So let me write it using another color. So the conclusion that we had before, since we know how to find the natural frequency that is equal to square root of k over m, right? So that will allow us to find m over k. M over k is something we need, right? So we have m over k over there. So m over k. So if we take a square on both sides, k over m, that will be equal to omega n squared. This is why m over k, that becomes 1 over omega n squared, right? And at the same time, we have a c over k in two terms. So we have c over k over there. We also have c over k on the numerator. So we want to find out what is c over k. To find a c over k, we need to start from the damping ratio, the definition of damping ratio. The damping ratio zeta, so this is my zeta. Zeta, that is equal to c over the critical damping constant, that is a c over 2 square root of mk, right? So from over here, we can find out what is a c over k. So we divided by k on both sides. So the numerator becomes c over k, and the denominator becomes 2 square root of mk over k squared. So that is m over k, right? So square root of m over k that is m over k, that is 1 over omega n, right? So this is how we can find a c over k that is equal to 2 times zeta over omega n. Let me rewrite it. So 2 zeta over omega n. So we're going to plug this into this expression over here. Now we'll continue from there. So that is equal to, the numerator now becomes 1 plus c omega over k. We have c over k over there. C over k will be replaced by 2 zeta over omega n. So that is 2 zeta over omega n times omega, right? And the denominator becomes 1 minus m over k. What is m over k? We already did that. It's 1 over omega n squared, right? Times omega squared. So that it becomes omega squared over omega n squared plus C over K, we already got that. 2 zeta over omega n times omega squared, right? So if we define the frequency ratio R as omega over omega n, we can find x over y becomes square root of 1 plus 2 zeta r squared over 1 minus r squared plus 2 zeta r squared. All right, we got half of the problem down. Let's see if we have any questions over here. No? Okay, pretty cool. So next we want to handle like what is the angle phi. We haven't done that yet, right? I'm not sure whether I can copy some information and paste it to the next page. Maybe this doesn't have a function like that, huh? No. Oh, I do find the limitation of a PowerPoint. It doesn't allow me to copy anything and paste it to the next page.
Professor?
Yes.
Does it matter if the base move in the same direction as x or in the opposite direction?
So if y that moves in the other direction, basically, right? So
yeah. If it's in the same direction or other direction as x?
It doesn't really matter that much. You can see y. If you think about a y moving in another direction, you can assume that a y have a phase angle of 180 degree. So if that has a 180 degree, basically means the sign of a y that is flipped.
I see.
Yeah.
Thank you.
That's a good question. Thank you. So next, we want to find out what is the angle of phi. So since we assume the solution to the equation of motion, mx double dot plus cx dot plus kx, that is equal to a times sine omega t minus alpha. We assume the particular solution or the steady state solution, that is x times sine omega t minus phi 1 minus alpha. And actually this phi 1 plus alpha become my new angle of phi, right? Omega t minus phi. So we know that a phi angle over here that is equal to alpha plus phi 1. But I still want to find what is my angle phi. So we already know that a tangent phi 1 that is equal to c omega over k minus m omega squared, right? And also the tangent alpha that is equal to minus c omega over k. So we can also assume that we know sine phi and a sine alpha. So from here we can also, this is equivalent to sine phi that is equal to c omega over this long term k minus m omega squared plus c omega squared. And at the same time, cosine phi is equal to the other part, k minus m omega squared over the same thing, k minus m omega squared plus c omega squared. At the same time, alpha, which is the same, sine alpha that is equal to negative c omega over k squared plus c omega squared. And a cosine alpha that is equal to k over square root of a k squared plus c omega squared. So this is what we have so far, right? So next, we know that phi angle is equal to phi 1 plus alpha. So this is something that I defined, right? I want to find the expression for this angle phi. So what I'm going to do, I'm going to find a sine phi and also cosine phi, right? So sine phi that'll be equal to sine phi 1 plus alpha. So we know how to do that, right? So that is equal to sine phi 1 cosine alpha plus cosine phi 1 times sine alpha, right? So we can do that. We can find a sine phi from doing this. So which will give us, so sine, cosine, so we have sine here, cosine alpha. So that will give us, so let's call this c omega over, let's call it a p. So this will be equal to k minus m omega squared over p. And this sine alpha will be equal to c omega over q. And cosine alpha will be equal to k over q. So let's do that. So that will simplify a little bit. So sine phi 1 times cosine alpha will be equal to c omega times k divided by pq. And the cosine sine alpha, cosine phi 1 plus sine alpha, that will give us the multiplication of these two. So that will be k minus m omega squared minus c omega divided by pq. So this is a sine phi. And a cosine phi, that is equal to cosine phi 1 plus alpha. That will be equal to cosine phi 1 cosine alpha minus sine, right? Minus sine phi 1 sine alpha. So we do the same thing. We bend that. So the first term is cosine, cosine. So the cosine times cosine. So it'll be k times k minus m omega squared over PQ minus sine phi 1 sine alpha, two sine terms, which are these two terms. So that is a minus c omega square. So that because we also have a minus sign, so that it becomes plus over PQ. Great, we are close. So now we have sine phi and cosine phi. We can find the tangent phi. Tangent phi is equal to c omega k plus k minus m omega square minus c omega over k times k minus m omega square plus c omega square. So look at the numerator. The first term is a c omega k. On the second term, we also have a negative c omega times k, right? So this term can be canceled out by this term times negative c omega. So that will leave us positive c omega times m omega square. So that it becomes mc times omega cubic. All right, we can also write it in the inverse form to find the angle phi. So phi, that is equal to the inverse tangent of this whole thing. mc omega cubic k minus m omega square plus c omega square. So next, since from the previous page we already learned phi, that is equal to the inverse tangent of mc omega cubic over k times k minus m omega square plus c omega squared. We want to write it in terms of the frequency ratio. So we will do the same thing by finding what is m over k, because we have m over k over there on the first term, right? We have m over k. At the same time, we have c over k. We'll do the same thing. We'll find a m over k and a c over k. Then we'll replace those, and then we'll be able to simplify that. We divided by k squared for both the numerator and the denominator. Let's see what do we have. So we divide by k squared. So tangent phi will be equal to m over k, c over k times omega cubic, and the denominator becomes, we divided by k already, so that is so k that become divided by out, so that we have 1 minus m over k times omega squared plus c omega over k squared, right? So this is what we have. Now again, we're going to use the conclusion that we have. So we know that how to find a natural frequency. Natural frequency that is equal to square root of k over m. So we can find m over k. M over k that is equal to 1 over omega n squared, right? And similarly, we can find a c over k from what we did from the damping ratio, c zeta that is equal to c over critical damping constant, so that is equal to c to over 2 times mk. So we can find a c over k that is equal to 2 zeta over omega n. So we're going to plug these values to the previous expression, then we'll be able to find tangent theta in terms of the damping, in terms of the frequency ratio. So tangent phi becomes m over k, that is a 1 over omega n squared, and c over k, that is 2 zeta over omega n. So that becomes 2 zeta over omega n cubic. And at the same time, we have omega cubic inherited from the previous equation. And on the numerator, on the denominator, we have a 1 minus m over k, that is 1 over omega n squared. So that becomes omega squared over omega n squared, plus c over k times omega. So c over k, that is 2 zeta omega n. So that becomes 2 zeta times omega over omega n squared. We can define the frequency ratio R, that is equal to omega over omega n. So that becomes 2 zeta R cubic, and the denominator becomes 1 over R squared plus 4 zeta squared R squared, right? You can further write it as a tangent phi, that is equal to 2 zeta R cubic over 1 plus, we combine the two R squared terms, so that is 4 zeta squared minus 1 times R squared.